Today we're going to talk about the development of the periodic table and a few periodic trends. First of all, you see here we have two different elements symbolized. We have oxygen, which is a clear colorless gas, and sulfur, which is actually S8, a solid. What's interesting about both of these is that they are in the same family in the periodic table. So there are a lot of similarities, such as the same electron configuration, similar reactivities, but they're very different substances. O2 is a diatomic gas. Sulfur has 8 atoms in a molecule, and it's a yellow solid. The properties are not identical, although very similar. When the periodic table was developed, we look at Mendeleev and Meyer. Independently, they came up with the same conclusion about how elements should be grouped. Periodic trends, we're going to look at 3 big periodic trends, and we're trying to rationalize those. The first we'll talk about in this video is atoms and ions and their sizes. The second, we'll talk about ionization energy, and then finally we're going to talk about electron affinity. To understand those, one of the first things we want to do is go over the concept of effective nuclear charge. In many electron atoms, another word for that is polyelectric, electrons are both attracted to the nucleus and repelled by other electrons, and those would be the electrons which are. So the nuclear charge the electron experiences, or the pull, depends on both factors. The positive charge from the nucleus and those shielding electrons that are between the nucleus and that atom. So the attraction of electrons to the nucleus depends on 2 things. 1, the charge of the nucleus. 2, the distance the electrons is located from the nucleus. For example, in large atoms, the electrons in the outer shells do not experience a full charge of the nucleus because their inner shells shield them from the nucleus. So distance is a huge factor. To determine an effective nuclear charge, we call that Z effective. Z represents the charge on the nucleus. What we basically do is subtract the screening constant. The screening constant is basically the number of inner or valence electrons. For example, if you look at sodium, core or inner electrons for sodium is 10. And so that would be the S. And when we subtract those, we get an effective nuclear charge for sodium of +1. And this would be the same effective nuclear charge for every element that's in family 1A. So would you expect an atom to experience a greater effective nuclear charge if it's a 2p electron in neon or a 3s electron in sodium? So what I do for that is I basically calculate the effective nuclear charge looking at the periodic table. Let's start with that for neon. Neon has 10 is the number of protons, so that's at Z, minus the shielding electrons for neon, which is 2. That's because the sublevel before, and if you subtract those, you get an effective nuclear charge of 8. Now let's go to that for sodium. So we said, and this is the one we actually just saw on the other side, we say sodium has 11 protons, so Z is 11, minus shielding electrons. So that means for sodium we'd subtract S for the shielding, and we end up with 1 for the effective nuclear charge. So for this reason, you'd expect neon to have a greater effective nuclear charge than sodium. So it would be the 2p electron in the neon atom. What electron would be closer to the nucleus? And 1s electron in argon or 1s electron in helium. For this, we also want to think of the idea of shielding. Both of these are 1s electrons. That means there are no electrons between either one of these atoms and the nucleus. So that's our first factor. So they're both 1s. The second factor is the number of protons. Argon, if you look at the periodic table, argon has, as we see, 18 protons. And helium only has 2. So essentially there are no shielding electrons, but there's a different number of protons. So argon has 18, helium has 2. So even though these are both 1s electrons, we would say the argon protons are able to pull that 1s electron in closer, and so the argon would definitely have its 1s electron much closer to the nucleus than that of helium. Let's look at another question. Now this one's looking at electrons within one atom. Germanium atom, which electron would experience the greatest effective nuclear charge? Now remember, if there's a greater effective nuclear charge, there should be less shielding. We want to pick out the atom or the orbital that has the lowest amount of shielding. If you remember these in the order, 2s is the one that's going to have the lowest amount of shielding of all these, because this would represent the 2s electrons, like these right here. Because when we go up to 2p, even those 2s electrons provide a little bit of shielding. And then when we go to 3s, that's going to have even more shielding. and 3p, even more shielding as with a 3d. But the one orbital so the answer for this would be 2s. Let's see, how would you calculate the effective nuclear charge from a 3p electrons are 3p. So first you look at, so we'd say 15, and then you want to subtract the core electrons from that, which is 10. The number of protons, or the nuclear charge, minus the core or shielding electrons gives you the effective nuclear charge. We're going to say Z effective is equal to the number of protons minus the shielding electrons. And so it would be 15 minus 10, so the answer should be plus 5. How do we get to the size of atoms? First of all, it's difficult to determine because the outside of the electron cloud is ambiguous. There's not a specific boundary where the electron clouds end. So what we do is we look at when two atoms are next to each other. If you have two atoms next to each other, we basically take the distance between the two nuclei, cut that in half, we say that's radius. If we have non-bonding atoms, we just say it's 1/2 the distance between two atoms when they collide. If we have two atoms that are bonded, we just say half that distance between the covalently bonded nuclei of those two atoms. So that's a radius. How does that affect size? Bonding atomic radius tends to decrease from left to right due to increasing effective nuclear charge. So what happens if you look at sodium, sodium is right here. Sodium is 1.54, then magnesium gets smaller, then aluminum gets smaller. So generally as you go to the right, they get smaller and smaller. Now the reason for that is as you go to the right, what is changing is the number of protons. So if we remember the formula, Z, which is the number of protons, minus S equals Z effective. What is constant as we go across a row in the periodic table is not the Z, but the S. We have the same number of shielding or core electrons as we go across. So for everything in sodium's family, we'd subtract 10 electrons, or 10. So for example, for sodium, it'd be 11 minus 10, which would be 1. Then for magnesium, it'd be 12 minus 10, which would be 2. And then for aluminum, it would be 13 minus 10, which would be 3. So as you see, as we go to the right, there's a much greater pull because those electrons that are added aren't shielding electrons, and so the nucleus pulls much greater on any electrons that are added. So that's a trend going to the right. When you look at a column, notice there's a big increase in radius as you go down. The reason for that is you're basically adding new orbitals. So if you look at hydrogen, hydrogen would be 1s, and then lithium would be 2s, and then we have 3s, and then we have 4s, and we have 5s. So each time you add another orbital, that consecutive orbital is going to be further away from the nucleus, and so it makes the next atom bigger. As we proceed across the row of the periodic table, the atom actually gets heavier, but the atom actually gets smaller. Are these terms a contradiction? Hopefully you'd say no, because you realize what's happening. The atomic weight is different from size. Atomic weight is basically in the nucleus. Size is based on the electron cloud. As you go to the right, we're increasing the number of protons, which is increasing the effective nuclear charge, and so atoms get smaller in a row as you go to the right because that extra pull from those added protons that aren't shielded by the electrons that are added. Order the following according to increasing atomic radius. Basically, let's go ahead and circle these on the periodic table. So there's germanium, and there's silicon right above it, and there's selenium, and there's chlorine. So let's rank these. We should realize that the ones in the lower period are going to be larger. So basically, these are going to be the two biggest. Now we have to figure out of these two, which is going to be the largest atom. Hopefully you realize it's going to be germanium because it's got a lower effective nuclear charge than selenium because it's got more protons. So germanium is going to be number 1, selenium is going to be number 2, and then next we're going to look at silicon versus chlorine. Of these two, silicon should be much bigger, so silicon will be our number 3, and then the smallest one should be chlorine because it's got 17 protons, the same amount of shielding, and so that's going to be the smallest. List these in order of increasing size, so we want to look at chlorine would be first, that would be the smallest, and then silicon would be second, so that would be the second smallest, and then the next one, would be selenium, so that would be the third smallest, and the biggest one would be the germanium. And so we check that actually is the correct answer. Awesome. Based on atomic radii, which of the following bonds would be expected to be the shortest? Now, if we look at this, we want to actually think of the idea that atoms get bigger as you go down a family. For this, if you look at hydrogen, hydrogen is simply 1s, and so there's two 1s orbitals that overlap. Then if you look at hydrogen versus fluorine, and bonded to fluorine, you have a 1s overlapping with that would be a 2p orbital. So we'd expect this to be much bigger, the number 2 to be bigger than the HH bond. Next, if you look at the fluorine-fluorine bond, that'd be basically a 2p overlapping with another 2p, so that would again be larger. And then the largest one would probably be the chlorine, because that's going to be a 3p overlapping with another 3p, where they're sharing those electrons. Definitely the smallest one of all these should be the overlap of the 1s orbitals. And so the correct answer would be the H2. Next question. Last thing we're going to do is talk about the size of ions. For this, we see that the ion size differs drastically from that of the neutral atom. Ion size depends on two things: nuclear charge, the number of protons, and the number of electrons, and the orbitals in which those electrons reside. So that's actually a huge deal. So let's look at the first one. The size of ions, specifically let's talk about cations. Those are the positive ions, and those are always smaller than the parent ion. So for example, if you look at lithium versus a lithium ion is much smaller. Well, what's the big reason? Well, you've lost one electron, same number of protons, and the outermost electrons is removed, and there's actually more repulsions now. And the other big factor is, for example, if you look at sodium, the outer electron that you remove is from a 3s orbital, and now there's no longer a 3s orbital, and the outer orbital for the sodium ion is a 2p. All of a sudden, you're at an energy level that's much lower. Next one. Let's look at anions. Now for these, we're going to again have the same number of protons, but we're adding electrons. So anions are always larger than their parent atoms. Those electrons that you add are actually repulsed. There's increased repulsion, and so that makes the atom bigger. And then finally, what happens when you look at a family? Well, as you go down a family, once again, this is the same as if you look at neutral atoms. You're adding energy levels. The size increases as you go down a column because of the increasing value of N, which would be the energy levels. So those. And the last thing we're going to mention here is something called an isoelectric series. Isoelectric is just a fancy word that means all the atoms and also the neutral atom are just going to have the same number of electrons. So for this example, we pick things that are isoelectric to neon. Neon, we know, has 10 total electrons. Configuration is 2s and 2p. Now notice these electron configurations that are written at the top are the ones of the neutral atoms. But what happens for oxide ion, this 4 is changed to 6, and for this fluoride, the 5p2 is changed to 5p6, and then of course neon stays the same. And then for sodium, you lose the 3s1, and then for magnesium, you lose the 3s2 because you've lost 2 electrons. Every single one of these atoms has electron configuration 1s2, 2s2, 2p6. Now, how does that size affect it? Well, notice since they all have the same number of electrons, the size is going to depend solely on the number of protons. But you have 8 protons, 9 protons, 10 protons, 11 protons, and 12 protons. Magnesium is going to be the smallest, and then sodium, and then neon, then fluoride, then oxide. The big thing is the ion size decreases with increasing nuclear charge, following according to increasing atomic radius. So let's look at these. Nitride, and so basically that's nitrogen, but we've added electrons basically so it's the same as neon. And then we've got lithium, but over here lithium we've lost an electron, so that's basically the same as helium. And then we've got carbon, and then we've got oxide. Now what we want to do for these is first compare the two ions together. We've got nitrogen and oxygen. Which one of these two would you expect to be bigger? Hopefully you would say that you would expect the nitrogen to be bigger because it has fewer protons. So the nitride ion should be bigger than the oxide ion. So that's the first thing. Now next, which would we expect to be the next smaller atom? And hopefully you think carbon, because notice we're still in a 2p sublevel. So carbon would be next, nitride, then oxide, then carbon. And lastly, lithium should be the smallest because when lithium loses its one electron, it basically only has one s. 1s2 configuration, so lithium's definitely the smallest. The order for this should go nitride, oxide, carbon, and then lithium. So I think the choice number 5 should be the best response for this one. And whoop, there we go. The best response for this one is number 5, and that's what we have right there. Next one, couple quick questions, which is larger sodium ion or sodium. Hopefully for this, you would pick the sodium because you have the same number of protons but a greater number of electrons, and sodium actually has that extra 3s1 electron. So the sodium is actually the biggest one for this because they have similar protons, and sodium has one more electron in a 3s orbital, and that 3s orbital is going to make it much larger. Let's do another one, which is larger, chloride ion or chlorine. Hopefully of these two, you would pick chloride ion because they both have the same number of protons again, but with chloride ion, there's going to be a greater number of electrons, and so you're going to have more electron repulsions, making it a bigger atom. See you tomorrow.